One thing changed my mind is this. Okay? I don't know how many of you know this. Maybe some Chinese, Asian students know this. It's the classical game from China called Go. I am a very amateur player, but I haven't played this for ever since college. So I know the game. I watch the news. I don't really play it. Even when I was playing in college, I was not very good. But I quit after one tournament when I lost after a 7-hour game. I decided my brain power is limited. I should never spend time on that. So I spent 7 hours, won the semifinal in the college level. Then I spent 6 hours lost in the final. So that was the last time I played this game. Anyway, so it's a board of 19 by 19, and each player take turn, white and black, you put one piece on it. And then if your colors completely surround the opponent's piece are taken away. At the end of the day, on the 19 by 19 board at 361 positions, at the end of the day, you count whoever has more pieces. It's a very simple game, right? Unfortunately, it has extraordinary complexity, and these are the bound the numbers I forgot to reference. The competition complexity of this, the decision tree, these are the estimated average game with 150 moves combined together is 10 to the 360 power. But if you play a longer game, way more than that, the longest game would have upper and lower bound of this. These numbers are pulled from Wikipedia, which you'll find the reference. I forgot to put the reference here directly. All right, so for the long time, this is one of the holy grail for artificial intelligence because, as we all know, computer can beat human long time ago in chess, and there's also Chinese chess. A very, very decent app on your cell phone would be extraordinarily difficult for many of us, most of us. You put on the expert, you would have no chance. Some of you may, if you're an expert player. But for this, there are AI application programs, to be honest. Before this thing happened in 2016, the world's best AI game, I can beat it blindly. Me as a really, really bad player, I'm not joking, not being modest, I'm not a good player in any sense whatsoever. And I never played against a human for 15 years. I can beat the best AI program in the world easily, okay? But then, come March 2016, came this news from Google, Deepmind. They developed AlphaGo. There were news before that they started to beat semi-professional players. Then they scheduled this game against the Korean guy who's the reigning world champion for the last 10, the best player for the last 10 years. But at the time when they started, he wasn't. He was number 2. But for the last 10 years, he was almost the god in this game. This generates quite some excitement. I, as an amateur fan watching this, among other some millions of people, I got up at midnight, watched this live stream online. In astonishment, watched this AI beat Lee in a completely dominant fashion. Right? So was at the very beginning was a lot of ridicule, a lot of doubt, suspicion when the professional player were commentating the first few moves. They would just go, oh, this computer is stupid. This is utterly stupid move. And we have no idea why it does that. 20 plays later, I said, it doesn't look so bad. 30 plays later, it's actually pretty good. And 40 plays later, that turns out to be something we never thought of. It was a brilliant move. And then, so it was a 5 game. They played the only game the computer AlphaGo lost was the 4th game when it was up by 3-0. The 4th game, as usual, the attitude has changed. People are paying attention because the AlphaGo was again dominating that game from the beginning. There was no every indication the computer was dominating, but in the middle of it, near the end of it, out of desperateness, he made a stupid, most utterly unexpected stupid move. He just literally he randomly threw a piece in there, and the AI, as the standard AI, somehow crashed and could not understand that, start to respond in the traditional AI way, and only 10 moves later start to come back, but the damage was too great. So so that's how he won one game, just because he did something utterly stupid. But it was eventually they discovered there was something along a bug in the way of design, an algorithm, but they start to fix it. But anyway, and then a year later, they scheduled a game against the #1 player, the 19-year-old Chinese Ke Jie, and this time was not even close. It was not even this guy actually literally cried after the game, says that he feels he's playing against Go God. Anyway, then they did something. Google did something interesting. They create a version 2, which they did not announce, but they just registered an account online, on the platform where all the pro player played. The account, the ID is called Master. They went on. Quickly, people found out this might be the computer AI because it's winning everybody. So eventually, it was 60-0 against every top player in the world. All the world champions you can imagine. Everybody went on and played against it. There was one draw, I admit. So Chinese media actually made a funny remark that Chen Yaohua, who was a former champion, gallantly made a draw against AlphaGo because they lost internet connection. All right. So, but officially it was 16-0. All right. So they retired in 2018 because there's version 3 came out that beats version 2 100-0, and then Google said we're done with this thing. All right. It was just an idea to test the power of artificial intelligence. So what's new in here, which was changed. This was shocking to me because I thought this was never possible. But what's different is that it's a different thinking as opposed to a traditional AI. When you search exhaustively all the decision tree to make the best decision, you give a score to each move and you find the best move. This is not possible here because the decision tree is the space too big. It's not in your lifetime. No computer can do that. All right. So what Google did is the opposite. Okay, it's almost like how human learns. It set a rule and let AlphaGo play against each other. All right. Then play this over and over again and try to learn what's the best way to learn. Among the number of games AlphaGo plays, it will, for every move it plays, it draws the probability of winning or losing. It assigns probability. If this 50%, then you just pick every move, pick the best probability. All right. For example, at the beginning, then probably all the viable choice at the very beginning probably has all 50-50, so it doesn't really matter much. But what's different is that now with computer, it plays against itself non-stop. At the time when it plays against Lee, I think AlphaGo has played against itself 3 million games so far. Among them, the first 30,000 games are all the record of every game human being has played. So what happens here so the AI here tries to decide the best move based on what it learned from the game it has played. So you can imagine at some point it gets better and better as it gains more experience, and that's exactly how human being learn things. In this, we have all the books to say in this situation you should do this, should do that. How do we decide that? Because human being has played 30,000 games. But AlphaGo can easily play 30 million, I don't know how many it has played now. So that's why now there's no way we can catch up. Based on this set of rules, it has the experience from this AI using deep neural network in conjunction with Monte Carlo tree search. The experience it has gathered along the way is orders and orders more than the entire history of human plays. So that's why eventually there's no way a human being can beat this. At the beginning when this designed, the 30,000 game from human history was part of this, and there was actually some general rules human had built that was built into AlphaGo, but it was astonishing in version 3 that there was no such thing. That all it had is the rule of the game, and the computer started to play among itself, against itself, and learn along the way, and now that's become a Go God. All right, so that completely changed my mind because I thought, okay, if things are so complex, but you can change your perspective, just learn along the way, and just make the best decision based on what you learned. And isn't that what we do? Instead of trying to exhaust all the possibilities to find the optimal solution. So then this paper by David Silver from the Deepmind team was published 2016. I have this book. Then in 2018, they published another paper on version 3. Okay? There's some technical thing about the deep network and the Monte Carlo tree search. So that got me started. I started to read many things. And of course, on the other side, you realize despite the amount of success, there's this thing that also create a lot of controversy. I'm not here to argue for it or against them. Just telling you this has happened. I'm sure, if not most, if not all of you have heard of this controversy. So anyway, this is a comment is made by Ali Rahimi in the NIPS 2017. So when I was giving a short talk in an Air Force meeting just last month, where Professor Zabar was also there, I was planning to do a short introduction of this thing. I was planning to make a slide like this, but then our friend called Houman Ohadi from Caltech the day before gave his talk. He put out this, so which is exactly the same message I want to give. So I thought, okay, why not? So I just asked him for the slides instead. So this slide is from Professor Houman Ohadi from Caltech. So despite this success, this deep neural network requires training. All right. The fundamental difficulty is that the structure of the network, how it works, why it works, is not so clear. There are many, many variations of the network. And then during the training, the different algorithm and the parameters to tune, and all this computational complexity and uncertainty built into that makes the problem very, very hard to reproduce. All right. What works for this particular problem, and you tune the parameters so hard, and if you change something, then it may not work completely. It's not that just it doesn't work as well by some close margin. You can get completely different result. That's what makes things so difficult. So Rahimi made this comment that the field has become alchemy, which is one thing is good, that because there's lots of work, lots of intuition, lots of experience going in. But then at some point, we need the entire field needs some systematic framework to elevate this to a new level, so alchemy becomes chemistry. That's how chemistry became. So there's nothing wrong with it. So take this as a positive message, means that there's a lot of work going on, but a lot of evidence just needs more systems. All right. So with this is what I was opposed to. So we started reading into some literature. So I will just talk about something we are more familiar with. So again, as I said at the beginning, just for the benefit of some of you who may not know all the details of neural network, I just put up these few slides as a short introduction. What are neural networks? Neural networks just it's a unit, massive parallel unit, that to mimic the functional brain. Okay? And here you can think of the circle as each neuron, and they are all connected together. There are layers and layers of neurons. Each layer can have a tremendous amount of neurons. Okay? So there's a very complex network. They are connected together. At the end of the day, they propagate information. All right? They propagate information for our benefit from some input that we receive, and the information is propagated through the layers and of the layers of layers of neurons. Eventually, come to the output. Okay, you can think of the in between. This is how our brain works. It is motivated by that, but it is by no means is a model for the human brain. Okay, these days, neural network has already taken on a life of its own. The purpose is not to do that. Okay, it's inspired based on the purpose now is to create a new structure to learn some input-output mapping. Okay, so now you think of input as some variables, number of parameters. So the input layer, usually the number of neurons is fixed. How many input layer? This is not neuron. It's really just how many input variable you have. And output, the M is how many variable you have at output. In between is the network. Okay, so this input-output relation is what we have as input and output. When we have data, we try to use the layers of layers of layers of this structure to reproduce this, and then in the future, hopefully to do prediction. Right? So what I draw here, the fully connected is a so-called fully connected feed-forward network. So every neuron is connected to each other, but connection only goes one way, nothing goes back. You can have this and go back to create a recurrent network, or there's also convolutional neural network, CNN, that works really well for imaging. There are many, many variations. But the fundamental unit in this is the neuron. So which is also the simplified model is so-called perceptron. Okay? So what I draw here is one perceptron. In fact, you think of this as perceptron. What it does is that it receives input. It receives input, again, you can think of it as input with n variables. Receive the input of this. You read this off your data with input variable. Then what this perceptron does is that it assigns weight to each one. So it weighs the importance of each signal differently. It finds the best weighting. All right. It finds the weights, then it does it takes a sum. It takes a weighted sum of this input variable, input signal. And then once you take the input sum, this becomes a single number. Even though this is multiple input, when each one has weight, you just arrive. The neuron perceptron is a very simple entity. It does one thing when it takes input, takes a variable, a single number, which is the weighted sum of input, and it decides what to do. The action it decides is whether it's active or not. So what's active or not usually is a step function. When it's less than some threshold, there will be a threshold or so-called bias that when it's less than that, based on the number, it can remain off like this here. Or when it's past bias or threshold, it becomes on. Okay, that's a simple mimic the neuron response to some electronic input. All right, so this is a simple thing. And then you put all the this does this simple on and off response, and you put many of them together in network. Somehow they can learn very complex structure. Okay? The simplest activation function is just step function. If it's less than some threshold, it will be off. Bigger than threshold, it will be on. Just jumps. Okay. This may seem reasonable, but mathematically or numerically, it's quite difficult because anytime we deal with a jump function, it's just there are a lot of difficulties. So people come up with different ways, some smooth version, and then so the simplest one, the step function, is also called binary. Then the sigmoidal function, basically just a smooth function connecting from one end to the other. There's some condition on that. And there's a bunch of examples of this activation function that have been used in neural networks. There's also ReLU, rectified linear unit. You can see I did this 3 o'clock at night. Right? Anyway, it's a simple function called max, 0, and this. So it's 0. When it's not activated, it stays 0. When it's activated, it's a linear function. It goes exactly like this weighted sum. So this is you can smooth this to get soft ReLU. But anyway, this is today is the most widely used activation function in practically all neural networks, including the Deepmind AlphaGo. This has tremendous success in practice. All right, so this is then you put, this is just response of one neuron. Then you put them together to create a network. So for simplicity, if we have just single layer. So this is what we call, so there's always input layer, where it's the input function x. There's always an output, where it's so if I want to model some function with D input variable, I would have D input layer, D's units in input layer. Then if my output is just one number, scalar function, then I would just have one unit at output layer. In between is the network here is what if you decide to have a single layer, this is what people call hidden layer. Anything between input and output are the hidden layers. You can do a single hidden layer function. Now if I do this, then you can, for single layer neural network, you can write down this simple expression. All right, it's basically you have a number of neurons. If I have n, 1, 2, 3, 4, 5, here's 5, and each neuron would take a weighted sum of input x. You give it every weight. All right, so it's become vector inner product. You arrive at a weighted sum, a single number. Then it depends on your bias. Okay, it depends on your bias, and you get a different number here. Then activation function will tell you how this neuron responds. It's on and off, or maybe in case of ReLU, gives you a number back. Then every neuron produces an output, on and off output, and another weighted sum, which is the coefficient here, would give you the final output. Okay? So for single hidden layer, single layer neural network, there's a very clean mathematical description on how this works. This, in many ways, you can draw a connection analogy to a standard approximation method like polynomial, radial basis. Basically, you have some sort of basis function that depends on x. That in it, there's some kind of wave number or parameter, and then there's an expansion coefficient. You put them together, you try to use to approximate some kind of function. Right? So this is what a single neural network does. Okay? A single layer neural network does. Turns out this is very powerful mathematically, and which sets as a foundation for deep network. But Then you have if we have a single layer, you can put the layers of the layer together, then you get connection. Right? So now you basically just, the structure I wrote earlier with weight and this, and now you just input layer. So every layer would receive input, from the previous layer. So I would say this is the first layer. That's the output of every layer of the first layer is just the input signal. Right? Then in here, the layer for every layer in between, the output would depend on the output from the previous layer times your weight function, weighted sum, get number, and the bias of each neuron in this layer, then act on activation function. This would be the output of this layer. Then for the next layer, another combination of this, and this goes on forever. Okay? Until we reach the last hidden layer, and then you just take the linear combination of this output, all right, and then that's our of the second to last layer, and then this final output. In the final one, usually you don't need the activation function. It's just a linear combination. That's it. All right, you could, but that's not. All right, so this is how deep network, the feed-forward deep network works. Okay, so usually you just write down this number. This denotes capital M is total number of layers. So then in between the M-2 is the number of hidden layers. And this number integer denotes how many neurons you have in each layer. So you can write down this single sequence number, and you understand that the structure of feed-forward neural network. Usually for deep network, you will have many numbers here, and each layer has many neurons here, a large number here. Right? What happens is that now inside each neuron would has set a weight function. Okay, the weight function depends on how many neurons you have in the previous one. So the weights are parameters, and the bias are also parameters that need to be trained. Okay, if you have a large number of neurons, the number of parameters between the weights and threshold it can be very large. Okay, this presents a very challenging situation for neural network, and that's widely acknowledged. Okay? You train parameter, there's nothing fancy here, just using available data, you create some kind of loss function. You try to minimize the mismatch between your prediction and the data. By minimizing the mismatch, you can tune your parameter in the model. Okay? This is essentially like a nonlinear, think of this highly non-trivial nonlinear least square problem. Okay? Nonlinear optimization. The most popular method is some kind of gradient descent, especially stochastic gradient descent. This was very popular because we need to mention this back propagation. Because when you do gradient descent, you need to know the derivative. Right? With so many parameters in this thing, the derivatives against every parameter is very hard to derive. So the back propagation basically says, using chain rule, you can loss function that you can write down the loss function, the derivative of loss function against the last layer, the weight function here. Then using chain rule, you can propagate this back. Keep writing chain rule. So the development of back propagation is a fundamental advancement that make gradient descent method viable for neural network. Then eventually, stochastic gradient descent become very dominant in this field. If you are interested, the so-called Adam method is also very popular. You go on Google Scholar, this 2015 paper already had more than 8,000 citations. And it's not even published yet, it's just in archive. Very useful method, okay, we use that also extensively. But again, the biggest challenge here is overfitting is one thing, because you have so many parameters, sometimes you can fit anything. You got so many parameters, you can fit all the data. That's called overfitting, because if you can fit all the data, you are fitting all the noise. So that's one challenge, but there are ways to address this. This is widely recognized. The problem with local minimum is also widely acknowledged, but harder to address, because we're doing this optimization in a huge number of parameter space. You minimize this function against, let's say, 10,000 parameters. And the loss function in the 10,000 parameter space would have very complex landscape. All right. Whatever optimization method you use, doesn't matter what it is, eventually it converts to zero derivative gradient. So one of the bottom of a well. Okay? But with so many parameters, there's so many such bottom, you can easily be trapped into a local minimum that's far, far away from anything reasonably close to the global minimum. But unfortunately for nonlinear problem, you cannot find the global minimum. If you have a linear programming problem, local minimum is global one, but nonlinear one, there's no such thing. So any method, you cannot get away. Any method, depending on your your initialization, you could easily convert to a local minimum that has nothing to do with the true solution. But then you look at derivative is 0, the iteration will not go on. And that's the problem. That's one of the reasons why a lot of complex problem training can, depending on parameter tuning, can give you a completely different result. Okay? And that's very, very difficult to address, even though there are a lot of effort in there, a lot of smart people working on that. Okay? And this also makes things very difficult that we try. Sometimes we thought, oh, we have some idea to improve such and such. And then we put it into some example, we cannot, and it doesn't really work. And we don't know if it's our idea is bad or just our optimization goes to some local minimum that we're just getting no result. We just have to abandon. We just couldn't test ideas very, very effectively because the optimization problem. But that's the, you can argue that's a separate issue, but it's really, really challenging to address this. All right, so this is also part of the reason makes a lot of heuristic go into neural network training. Okay, having said all this, we say this field has been very heuristic. There's a severe lack of rigorous math. I would like to just, actually there's quite a bit mathematics in this. So this is an incomplete list of what's in the literature. Most mathematical study focus on feed-forward network. It's just easier, and with one hidden layer, just like that, which we have a very simple expression that makes it more easier to do theoretical analysis. One major effort is to show that this expression is capable of modeling any function. This is called universal approximator. Traced all the way, and most of the fundamental work was done in 1990s. All right. The most famous paper is Pinkerton in 1999, which is a review of the work up to date. You can see this paper even today is of significance because the most important work was done by then. But there's still a lot of variations that depend on mathematical details people try to study. So this field is still ongoing. We'll briefly talk about this in a moment. Then, as I said, the other one is one thing to show, to prove that this thing is capable, approximating anything, but it's another thing to show at least there is one. So people try to come up with a construction that should at least have one that is capable of approximating something. Then this is what we call constructive proof. Right? It's an explicit construction of a neural network that you don't need training. Every parameter is defined as such and such, and you prove it's that. It's just like in polynomial interpolation, we have a very precise formula that. Right? There's nothing really different on the fundamental level. You construct something to show that it's capable to approximate. This is one of the earliest paper. I don't know how to say this French name, but let's just call this CE operator. It's based on, it's a one-dimensional operator. One dimension means it's approximate function of one dimension on the real line. Okay? Since then, there has been quite a bit of work along this line of approach, try to extend, analyze, and do some variation of this. I have the dot here, means all of these are going on. The work by Anastasiou actually starting in 1997. Actually, we found his paper even today. So it's still quite active. I would later focus a little bit on this. This is the incomplete list. Okay. Then there's also Ridgeless transform by the very well-known applied mathematician Immanuel Candice. In fact, in his PhD thesis in 1998, he has a very complete framework based on what he called Ridgeless transform, so that can show single neural network can approximate any function. This doesn't need to be in 1D. Right? It's a multi-dimensional function. The challenge is that it requires an activation function that's not available in any neural network. It's a very specific activation function. So actually, it doesn't really match what we have in practice. So very recently by these Japanese authors, just this year, extended this, sort of relaxed the requirement they need on the activation function. So at least now you can use ReLU, some other activation function, but then the inverse transform becomes extremely difficult to understand. But anyway, these are some theoretical work. There's also another line approach by using homograph representation theory. This is very specific for deep network. Try to understand things, understand functions as computational functions. Right? In 1992, there was a theoretical development to show deep network somehow mimic the structure of homograph representation theory. Then, more recently, a Spritzer tried to construct a network that mimics this theoretical foundation. In fact, he has a more recent paper in 2014 on this. These are very, very complex. So they serve mathematical roles, not much. And then there's also the thing very specific design for ReLU, that rectified linear unit. Using 3 ReLU, you build a hat function. Deep network translate back to the input layer, it becomes multi-resolution wavelets. All right, that's more recent. All right, so let's first talk a little bit about what does universal approximator mean. Okay, it means that this can approximate anything. So again, for single hidden layer, you can write down this neural network response. Okay, weighted sum of your input, the weights are AI. Then based on threshold, based on bias and your activation function, decide the action on and off, produce a number, then take another set of weighted sum to get the output. Then you try to match input-output relation. This was summarized in this paper, was very nice result. Basically says this expression can approximate any real function. Okay? In mathematical way, it just says this. If I take this expression, take the span of this, basically said any possible combination of this with C's and A and B's, then this span, if I take A being all the real number, B as all the real number, and then this is dense in CR, means that you can represent any continuous function with any arbitrary accuracy. Right? So which was very, very useful as a fundamental belief to use this kind of construction. There are many, as I said, there are many, many extensions, variations on the mathematical side ever since this work. So, but it's a different story to show how this works in practice. So I'm just going to write down these a few operators. Okay. The actual formulation is not important, but what's important here, I would emphasize 2 things. This original operator is on the real infinite domain, so R to R. Okay? Costarelli-Spitzer result in this is on bounded domain. There are other constructions, but we found this one to be a little bit more practical. On this unbounded domain, and they all based on equal distance node. You put a uniform grid there, you read off a function, you can immediately write down this expression to try to construct things. Okay? This, for example, here in this work is you prove this is at most first order accuracy. Okay? It doesn't matter how smooth your function is, this gives you first order. But turns out this is where we did a little bit more detailed analysis. Turns out this you can get something better, that for anything that inside the domain. If I take any bounded interval in the domain, you can always find second order convergence if you have enough neurons. Okay? So it's better than that. But the fundamental thing is that there is a boundary in this case, which you have no idea how to fix it because the problem doesn't have boundary. We don't know how to fix that. So I can make this second order inside in the interior domain. Once you decide where the interior is, I can always find enough neuron to get you second order. On the contrary, for any fixed neuron, I can always break this order near the boundary. So this one actually, we have a theorem on that this approximator has an upper bound of 1.5 order. You can never go beyond that. Despite of that, it can still be very useful. For example, if you do some piecewise continuous function that have jumped, which is notoriously difficult to approximate by standard method, you get Gibbs oscillator. This one has no Gibbs whatsoever. Okay, I will just caution that. Here, you may have second order. Right here, you lose your accuracy quite a bit, even though there's no Gibbs. So for any effort to try to solve this with PDE, I would be very, very cautious. In fact, we tried that. The moment you take a derivative, it just doesn't work. But it's a nice thing to have decent accuracy, but not good enough to solve PDE. Okay. All right, so let me show you. So then let's just do, what if this is just focusing on real lines? So what if I do function on multi-dimensional? Because most functions are not on real lines. Okay? So then you can take all these earlier results, they have been done. They just do tensor product. I have one-dimensional operator. I'm just doing tensor product. This is nice. It's good because mathematically you have a rule that give you approximation in multi-dimension. In practice, this is useless because in high dimension, you have so many points. It's not useful. So, so let me show you something. We recently do a very simple network that can do multi-dimensional function approximation in a very simple way. I will have two hidden layers. The first hidden layer have n times n minus 1 neuron. Little n here is number of data. It's not a number of anything else. It's number, depending on how many data sample you have. In the first layer, I would group into n groups. Each group have n minus 1 group. And then in the second layer, I have n little n number of neurons. I connect them together. Then we very specifically define the weights like that. All the weights and bias are dependent only on the location of the data. The moment you have data, you know where the data is, you know the weights and bias, and you use exclusively only the step function, the binary, to come up with this weight, and then eventually come up with this, and you can prove that this gives you a piecewise constant approximation for any function based on your data, and if your data, any data you have would give you a Voronoi tessellation, and this neural network does that. It conduct a Voronoi tessellation and give you piecewise constant in each cell. Okay. We know Voronoi tessellation is the domain that separating the closest point from each point here. So anywhere here, a point here is closer to this than to the other one. Okay. So you put this in practice. I only show you 1D result. This works for any 1D. You would get a piecewise constant thing. You have enough neuron, things would not look so flat. We deliberately use only 30 neurons to show the piecewise constant feature of this thing. All right, but as I said, all of this is not really useful. I mean, they are good mathematical exercise because in practice, people don't do that. People do this. I'm sure many of you who use this, you have a neural net, you go in, you train it. You never try to define your parameters. And sometimes you just use TensorFlow. You don't really know what's going on inside. But inside, it's a training, try to minimize cost function with some kind of gradient descent method. All right. And we did this thing that we try to reduce number of parameters to train. So this is specifically applied to ReLU network, which is the most popular network. So let's look at ReLU single layer. Just start with single layer. This works for multiple layers. If I write down my ReLU net single layer, I would have an activation function. We're assuming you have activation function has this scaling factor. If I have a positive number in this inside, you can pull it out to become different factor. This factor does not depend on the location. It's a constant. So ReLU certify this with exactly alpha. You can pull it out. Or step function, another one will certify this as this is constant 1, never changes. All right. Either way, this both certify this. Then we say if you can train your network, like if you train the network based on some kind of optimization, that is an equivalent form of this. I change this to W here, but the weight is unit. The norm is unit, is 1. Right? Okay. And then so this is very simple to derive. If I have an expression like this, I would just take the norm out of this as a factor, put it here, and put it up front, and this is a constant I just redefined. So it's a very simple way to see that. It's nothing surprising here. But what this does is that you have if you train something for W in the entire space, now you train on unit sphere. Okay? It's very restricted. Your search space becomes much smaller. Okay? So then effectively you reduce one parameter because you're not in the D-dimensional space. What's more important and what's subtle is this result. Actually, this makes a bigger difference. Is that, again, you have a neural network if you train like this with a weight in the entire space, with a bias on the real line. You have an equivalent form that this have unit 1, unit vector. At the same time, your bias is in a bounded interval. How big is bound depends on how big your domain is. All right. Usually you have function in the fixed domain, so you have this bounded interval. Turns out this bounded interval would have a tremendous improvement on the training result. I will show you the result later, but before I show you the result, let's give you some mathematical justification. The original training of network would be in this space. I span my activation function of weights and bias, both are in. So standard one, weights would be the entire space, bias would be on real line. And with the two constraints here, let's just go here, I can constrain this to a sphere, unit sphere, and I can constrain bias into the bounded interval. You can prove that this space are equivalent mathematically, and you can also have all these things about dense in continuous function basis sets. I can have these two constraints, one on unit length on the weights and one on bounded interval on the bias. You will get a mathematical equivalent thing. You're not losing anything, even though your parameter space becomes significantly smaller. Okay? Then you can, the same principle you can apply to deep network to go through that. You get very similar condition. On every layer, the weight needs in each neuron is a unit vector, and then the bias is slightly different depending on what you use. If you use a ReLU, then that's a factor of 2 to the power, depending on how deep the layer is. If for binary, it's actually simple, just fun. All right, let me show you some example. This is a very simple approximate, just for sine function. We do a very simple test so we can see. Our training data, quite a bit of data. This is by 40 neuron, I think. Again, this the unpredictable nature of training. Depending on random initialization, the red is obviously the exact function. You could get training like this, which is completely off. I'm plotting some of the worst results. Sometimes you get fairly good approximation. But this depends on the initialization. If we use exactly the same initialization gives us this, apply the constraint here. Let's just look at this constraint where we constrain the weight and bias. This is only constrain the weight. You get a much better result. This is with exactly same random initialization of parameter, then with the same solve. We didn't write the solve, we just used MATLAB. Okay? And then this conversion history. Okay? So this also works with multiple hidden layers. If I do 2 hidden layers with 20 neurons in the first one, 10 in the second, again, I pick one of the worst results. You train this standard way, no constraint, you actually get 0 out of this. This tends to happen. Okay, this is where people do a lot of things, leaky, ReLU kind of thing to get rid of 0 derivative. But I take exactly same initializing that produce this result, just add constraint here. You get much better function approximation. Different initialization sometimes give me this, again, way off, and but this same initial condition, if you just add that constraint, you get much better result. Okay. As I said, what's not obvious is actually the constraint on the bias plays a much more important role on the constraint on the weight. This is a 2-dimensional function, a Frank function. Frank function is a collection of 4 Gaussian. You look at the contour plot here. All right. If I do single hidden layer again, this is the red line at the exact contour of these Gaussian bumps. These are like 3 hills. And you can see the new training result goes like this. And if I take a cut here, that's the just cut along this line is this. But if I add a constraint, this would be much much better, visually much better comparison than this. Okay, and then cut here. Then let's do a deep layer. Not deep. Okay, I only have 4 hidden layers. 10, 10, 10, 10. 2-dimensional function mapped to the outwards to the map is 2 to 1, but 10 layers in between. Again, some initial conditions give us a really bad result here. Okay, the contour nowhere match the real one, but at this constraint, same initial condition, at the constraint, the result become much better. I think I'm running out of time, but let me just finish. Just show you a collection of our very limited research on this. It's a little bit scattered, but so I try to put them in a coherent way as much as possible. If it's not, please pardon me. This is, to me at least, or to our group, my student and postdoc together, is a very exciting field with many open issues, but nothing is easy because a lot of smart people have worked on this. But there are some math to be done, especially the parameter reduction thing we did has actually for once a little bit practical. We have shown this for some training more than the result I show you that really improve the training result. We're working on to apply the same principle to a convolution network for imaging, but we're not there yet, but we're still working on that. So with this, I think I have 15 minutes. Let me stop. Thank you.
Thank you. Any questions we have? You will have to repeat the question for the microphone to pick it up.
Okay.
So open for questions. Steve is always volunteering for all the questions.
So we showed that we can approximate functions. Can you tell, first part of this question is, can you give us a little bit more detail on the sorts of functions that we can approximate? And then the more important part to it is, say I'm doing reinforcement learning. The function that the neural network is learning is a policy for how to act. Can I put meaningful constraints, say, on what policy I might try to learn and improve my ability to learn it?
Well, so the first part of the question is the source of the function?
Yes, can you tell me more of the properties of the function that makes statements about being able to approximate a value?
Oh, okay. So the first is about the property of the function that the theory now says we can approximate. Usually, so far is the earliest result where I quote a theorem that it's just continuous function. Okay. It's a continuous. But as I said, there are many variations. Later, people talk about difference in different regularity, how many derivatives you have in software space. There are more work on that. There are a lot more theory on that. I only quote the very earliest one. Says neural network like hidden layer like that can approximate any continuous function to arbitrary accuracy. So that's the earliest result than other things. So that's the source of function. If you want different property of that, you have to go into the different paper. They have different assumptions, different analysis tools of that. The second part about policy making, reinforced learning.
Right. So if it's easier to get a meaningful approximation of a function if I constrain higher derivatives of it. Is that, can the statement be made like that?
So the question is if one can make more meaningful or training result if you can combine combine maybe more information like derivative. I think philosophically, yes, of course. If I have more information, more derivative. Here I don't know. But we do approximation theory, and in a standard way a lot. We know if you have derivative, you can always get a better result. You get no worse result. Okay. You have, unless your derivative is bad. Okay, noise. So which is a tricky situation because noise in derivative is actually makes the result more sensitive. But on a philosophical level, yes, more information is helpful as long as you have a good handle on the noise. In neural network, I am not aware from a mathematical point of view using derivative. I think there might be 1 or 2 papers. I could not remember clearly. So, okay. But in a larger context, decision making, I'm not aware of. I did not. There are too many papers to read for me. So,
thank you.
Yeah, thanks for your presentation. I have a few questions. So the first question is, if we for data input-output relationship, so do you think the single layer network works better than the maybe 2 layer or 3 layers?
So you're asking if we have input-output relation from data. Yeah. A single layer works better or deep? The consensus is deep network works better. That's what makes everything the explosion of deep learning with neural network is because deep network is capable of learning very complex phenomena. I don't know why, because the theory says single layer is enough. That's the theory. But for very complex phenomena, you need many layers. How many layers, how many neurons in each layer, that's a wide open question. I don't think there's a clear answer. Okay. But in general, deep network is more powerful.
Okay, thanks. So how to quantify the uncertainties from the input to output?
You ask him. I don't know.
So in the same line, are these constructions robust noise in the function evaluation that you provide?
Robustness, sensitivity, there's been some loose discussion, at least as far as I can see. I don't know. There's no systematic study so far. So there's no, really no. I've seen recently some work try to understand deep network as a dynamic system and try to understand stability. I don't know. It's too early to tell. So not anything systematic that I'm aware of.
We have,
Again, I didn't read anything, so.
I have a question about the activation function you're using. You mentioned in several places that the binary.
Right.
How do you use that? Because the problem was people use the sigmoids and so forth because you can take the derivative.
Right, right.
So if you use the binary,
You can't.
how do you cope with the optimization?
That's why people don't use binary a lot.
Yeah.
That you answer your own question, yes.
You said about the deep learning, how many layers? It's 18 actually. That's what Google uses.
Okay,
Why
okay.
18? My theory is that 8 is a lucky Chinese number, so you get a 10 there, you get 18 as well.
That's good theory. I'll buy that.
I have a question. So, if all the activation function in your network is ReLU, is this network still nonlinear?
Yes, the question is if the active function is ReLU, is it nonlinear? It is. ReLU is a nonlinear function. That is a linear part is two piecewise linear part makes it, this itself is nonlinear.
Yes, so if the network has all ReLU, will it make easier for design a specific like a constraint to optimization? Will that make it easier to interpret what happened inside the network?
What's easier? I didn't
Will
get.
it make it easier to interpret what happened in the network?
Using ReLU or not?
I mean, if the network has all ReLU activation function,
Uh-huh.
will it easier to interpret what happened in the network?
If the network has all ReLU function, would that make it easier to interpolate?
What happened?
What happened?
Yes.
interpret.
What do you mean? What happened? It's just interpret. Most the network we use are all ReLU.
Yes. Is it more clearly mathematically represented?
I don't know about the more clear. At least all the mathematical papers are assuming the same activation function most. So you're trying to. Are you asking if one makes different activation function?
Think of two-layer network.
Right.
If you use a very complex activation function,
Right.
if you write the expression out, it's very complex. But if the activation function is just a ReLU, writing the expression of a two-layer network is not too complex, right?
What do you mean complex? I mean, the function can be complex, but the computer is just evaluate things. So the complexity of activation function, I didn't think that has anything.
Any difference?
No, I don't think. It's the smoothness that you can take derivative or not, that makes a difference. There are many sigmoid functions with hyperbolic tangent that they have. People tend to use easier function. You can use complex. In fact, if you use that Japanese work on Rigidate, that one has an extraordinarily complex activation function in the inverse, which takes, let me remember, second derivative of Hilbert's transform of Gaussian function. I don't even know what that is. So,
Oh, yeah. Get that point.
okay, yeah.
So
But
when the activation becomes complex, it do not necessarily mean the network is more complex. So
I don't think so.
make it easier.
I don't think so. I don't know if there's a theory on that. I don't think so. But.
And there was a last question down there,
Yeah.
if you're ready.
How do you manage the challenge between effectiveness and computational capacity of neural networks? Like cost of computational capacity.
How do I balance the challenge between the complexity and the cost?
Yeah.
We do that. We just solve very simple problems. That's how we balance. Then there are a lot of smart people out there. They balance their own things. We just sign function. That's all we do.
It's an easy way.
It's very, very challenging. It's very challenging.
With that, let's thank the speaker again.
Thank you.